to enjoy your lessons, then you must be on Joy Learning channel. So you are all welcome to today's lesson. So if you can hear me loud and clear, today's lesson is on orbital shape and electron configuration. What do we know already about this topic, electron configuration and orbital shape? Right, so we want to visit or remind ourselves of what we know already. If you can hear me, share with us. As I said, if you have a noisy background, please don't turn on your audio. Otherwise, it will get the class. So make your contribution, then you turn off your audio. What do we know already about the shapes of orbitals? The shapes of orbitals, what do we know already? So share with us. Yes, I'm waiting for your feedback. What do we know about the shape of orbitals? Hello, Sam. Hello, Sam. Hello, Sam. Can you hear me? Hello, Sam.
Yes.
Yes. What do you know about the shape of orbitals? Hello, Sakina. Sakina. Yes, Sam. Please use your name to sign in so that I will know your name. Salom Tete. Hello, Salom Tete.
Sir.
Yes. Tell us about the shapes of orbitals.
Can you hear me?
Yes, please.
I think the shapes of orbitals are under atomic structure.
Okay. So what are they? What are they? Mention them.
Hello.
Yes, mention them. Salom, mention the orbitals that you know.
They are the K, L, M, N, and the O.
Okay. In quantum numbers, what are the shapes do we have to know?
In the presence of the quantum numbers, each shell can hold a maximum number of electrons given by the formula 2n raised to the power 2, where n is the shell number, or more correctly.
Okay. So if we are talking about the K and so on, we have orbitals within those shells that you have just mentioned.
Yes.
So name the orbitals within those shells.
The K shell.
Now you mentioned K shell. So if I have
Yes.
the nucleus here, this
Yes.
shell is nearer to the nucleus, and that is the K shell, isn't it?
Yes.
Within this K shell are located orbitals.
Yes.
With reference to quantum numbers, what is the name of the orbitals in the shell K or in the K shell?
Electrons.
No, I said the electrons are in orbitals.
Okay.
So what is the name of the orbital that is containing electrons in the K shell? Okay, that's good. Salom, thank you for your contribution.
Okay.
Thank you for your contribution. Please use your name to sign in so that I can mention your name to answer questions. And then please share the link with your friends so that they can also come on board. So together we learn.
Okay.
Off your audio if you have no contribution to the class. If you want to ask questions, you on the audio, ask the question, then you off the audio for me to answer the question. That is our rules for the class. So everybody off your audios so that the class will be quiet for us to hear what I say. Okay, so from quantum numbers, you talked about the S orbital, the P orbital, the D orbital, and then the F orbital. But for the purposes of today's teacher and you, will talk about two of this, the S orbital and then the P orbital. This is what you have to know at this stage of your education. So the question is, how does the S orbital look and how does the P orbital look? So that when I see a diagram of the S orbital, then I should recognize it. And then that of P, you can also recognize. So let's look at the S orbital. So this is how the S orbital looks like. It is spherical. And then, of course, they are into axis. We have the X, Y, Z axis, giving it a three-dimensional view. So the S orbital looks spherical. So if you go to buy balloon and you inflate it, it looks like the S orbital. As you can see, it is round. It means that it has no direction in the axis as shown. So I can say this is my x-axis, this is my y-axis, and this is my z-axis. Now the orientation of the x orbital is in space. So irrespective of whichever axis you label as x, y, z, it doesn't make you wrong. However, you are going to label the axis is correct. So that if I have this, that, and I say this is z, that is x, this is y. I have the s orbital like that. What you have here doesn't mean it is wrong when I compare it to what I have here. So this one, there's nothing like memorizing it as this is how it should be. No, it's in space. Follow carefully. So we can describe this, and you can see this label here as the node. The node is the space around the nucleus where there is zero probability of finding electrons, or the probability of finding electrons at the nodes around the nucleus is zero. So don't forget that. So anytime they talk about the s orbital, please, the s orbital is spherical. And of course, it increases as the size of the atom increases. So it becomes bigger and bigger and bigger. Just as I gave an example of the balloon. The more air you blow inside, the bigger it becomes. So if you want it small, blow small air. If you want it big, blow more air. And don't forget, as you are moving away from the nucleus, the s orbital becomes bigger. And the electrons located in them also increase in energy as you are moving away from the nucleus. So I can say that as the s orbital increases, the energy of the electrons will also increase. So let's look at them in context. Hello, please off your audio so that your background noise will not disturb the class. If you want to ask a question, turn on your audio, ask your question, then you off it, so that when I speak, you can hear me loud and clear. Is that okay? So the characteristics of the S orbitals, I have mentioned some of them already. We said that it is spherical. And I was talking about quantum numbers. If you have studied quantum numbers well, then we can say that this L here is 0, and the M sub L is also 0. Number 2, it has no direction. Please off your audio if you have no question to ask. If you are not contributing to the class, off your audio. And I also said that use your name to sign in so that I can mention your name to answer a question. And then also share the link with your friends so that they will also join the program on Joy Learning channel, Teacher and You. Now, today it is you and it is me with the one in here. And then I have few names, let me mention them. I have, please, the ITEL P17, please kindly change that to your name because I want to know your name. J Redox, please change to your official name because I want to know your name. Then I have Jeshurun Sam, that's good. I have Samira there. I have Salom Tete, I have Bochi. So I want to mention your names so that Joy Learning will take note of you as one of our friends. So you can also decide to send in chats or on questions and so on and so forth. Right, so let's continue. So the S orbital has no specific direction. And then number 3, successive S orbital differ only in size as n increases. So n from quantum numbers, you know it as principal quantum numbers. So every shell, as Salom mentioned, the K shell, the N, and so on. And so on, contains orbitals. And the first one in every orbital is the S orbital. Please send your details to us so that we can follow you in your learning program. Your name, school, location, and telephone number. So that we can call you and say, oh, Salom, how are you doing in school? Do you have any challenges that we can help you in chemistry, physics, biology, commerce, integrated science, all the subjects that you are running in school? Joy Learning will say, oh, Salom, if you have any problem, let's help you. So if it is chemistry, they will say, with the one, Salom has a problem, so please help him, and I'll be glad I do. Okay. So that is the increasing energy of the S orbital in atoms. The next one is the p orbital. The p orbital is a dumbbell. You have dumbbell in your home, in your kitchen. Hello, Salom. Are you there? Hello, Salom.
Yes, I'm there. I'm here.
So do you believe that you have a dumbbell in your kitchen, or the shape of P orbital in your kitchen? Let me draw it for you to see if you can recognize it. Do you have something like that in the kitchen?
Yes.
What is that?
Yes.
What is it?
A dumbbell.
Do you have it in your kitchen? Not in your gym. I say
Yes.
kitchen. Why? What is that?
Is it the one they use for exercise?
No, not that one. The one in your kitchen.
Yes.
Kitchen.
Yes.
So recognize that, identify it. Salom, you don't help mommy in the kitchen.
I'll say it's a P orbital.
Yes, and I'll say that. Do you have something like a P orbital in your kitchen?
Yes.
So identify it. What is it?
I don't really know the name.
It means you don't have mommy in the kitchen. Okay, thank you so much. Yes, Samira. Okay. Hello, Samira.
Hi.
Samira, please. You have P orbital in your kitchen. What is it?
So no idea.
Ooh, Samira, I hope you help mommy in the kitchen.
Yeah.
And then it should be, you have been using it. I'm sure even today you use it. I'm sure even today you used it.
Nice.
James, listen. James, your hand.
The grinding. I don't know how to say it. I don't know.
The one you used to grind. Thank you. You got it there. James, that's excellent. That is tapoli in our local language. We use it to grind pepper, we use it to grind tomatoes, and so on. Samira, are you there?
Yeah, yes, please.
Have you recognized it now?
Yeah.
Samira, are you at home right now?
Yes, please.
So show it to us. Go and take it and show it to us. Tell mommy you want to show this for us to see.
Okay, a minute.
Thank you. That's excellent. So Samira will show us the tapoli as we have been using it in our homes. So that's a typical P orbital. Yes.
That's why I was saying that I didn't. That's why I was saying that I didn't know the name of it. I didn't know the English name of it.
I don't even know the English name. All I know is tapoli. Tapoli.
Yes, used for grinding pepper.
Yes. So what is the English name?
I don't know the English name for it.
Okay, so please, that is your assignment. Salom.
Okay.
Salom, send the answer to Joy Learning channel, okay?
Okay.
So when you find the answer, this is to all of us. Me, myself, I also go and look for the English name. So when you find it, send it to my Joy. Okay, so my producer will send the email to you so that you can email the answer to us. Okay? Hello.
Okay.
Yeah, Samira, are you back?
Yes, sir. Yes, sir.
Please show it to us. Turn on your video and show it to us.
Okay.
Thank you. So Samira is here with the tapoli. Can we see? Can we see? Samira, please raise it up. Raise it up for us. Can you see the tapoli? Salon, can you see the tapoli?
Yes. Yes, please.
So that's a typical p orbital in your kitchen. You see the beauty of chemistry. So we use it to grind pepper, tomatoes, and so on when we are preparing food. Then, when Salom was young, he followed the mother to the market, and then he was crying that the mother should buy pawpaw fruit for him. Then mommy bought one for him. He said, no, as for him, he doesn't want one, he wants two. So mommy agreed to buy two for Salom. So as he was playing with it, he put the two pawpaw fruits together at their ends like this. Like that. So if you put two pawpaw fruits together from their ends, it also forms a dumbbell shape that is representing a p orbital. Are we there? Hello? Then the
Yes,
other
we are
time,
here.
thank you. Please, if I call respond, if you respond, it means that you are really following the lesson. Then the other time, Samira was crying during the Salah break. So she was crying that she wanted a balloon. So mommy bought the balloon for her. And after inflating it, she tied the middle of the balloon. Like that. So balloon tied in the middle will also form the shape of P. Are you there?
Yes, we are here.
Yes, we
Salon.
answer.
Salon, what other example from everyday life can you give to represent the p orbital? Everyday life. Look at the fruits, pawpaw. I've given that example. What others? So mention one fruit for which if you put them together at their end will form the shape of P.
Avocado pear.
Thank you. That's excellent. Yes, you are following the lesson. That's excellent. So that is p orbital in everyday life. Samira, you are laughing. So Samira, you need to give one fruit that when you put the two together from their ends, it will form a p orbital.
Yes. Yeah, said mine like.
Yeah, I said yours.
Yeah.
Oh, okay. Let me look for a different name. Please use your name to sign in so that we want to know your name. Joy Learning, we want to know your name. Ike. Oh, no, not Ike. Is it like Boche? Hello, Boche. Boche, I can't hear you. Turn on your audio. Turn on your audio.
Hello, sir.
Boche, give us one example of a fruit that will give us a dumbbell shape representing p orbital. One fruit.
I think Popo, I have no.
Popo, I am giving that example. That example is my own. So give us one.
Okay, so I just joined, so I want to know more.
Okay. So you are welcome. Please use your name to sign in. Yes, use your name to sign in so that I can mention your name. Enjoy Learning will take note of you. So, what about pineapple? What about pineapple? Will you agree to that? Boche, will you agree to that? Pineapple.
Yes, sir.
Pineapple
Yes, sir.
is also,
Yes, sir.
Yeah, pineapple is also a good example. Okay, so now let's look at the characteristics. So please, chemistry in action, we can identify p orbitals in everyday life. So let's look at the characteristics. So number one, the p orbital has a dumbbell shape. As we have already discussed, we can have a shape is like two spheres touching at their edges, or inflated balloon tied in the middle with a string, or two pawpaw fruits put together at their ends. Then we also talk about pineapple. Ceylon talk about the Avogadro pear, if you fix them. So as we have learned today, if you close the class, go and buy two pawpaw fruits and then put them together at their ends and see the beauty of the p orbital. Or you go and buy Avogadro pear, put it together at their ends, and you see the beauty of the p orbital. Number two, the orbitals are perpendicular to each other in space. So if I have
this,
yes.
What about two cucumbers?
Two
cucumbers.
Cucumber.
Yeah.
Two cucumber.
Yes, sir.
Yes, I think it's also a nice example.
Okay, sir.
Yes, I think it's also a nice example. So the p orbitals are perpendicular to each other in space like that. Please, you should learn how to draw the p orbital shape. Then number three, orbitals are directed along the x, y, and z axis in space. So I can say this is z, that is x, that is y. So always you have to show the axis. If you are drawing the p orbital, you have to show the axis. So I have I have y there, z there, x there. Then you draw like that. Learn how to draw them. Then, as we have already talked about S, P also increases in size as the size of the atom increases. I'm talking about the size of the atom because we said that as the principal quantum number, that is the energy levels increase, the size of the atom will increase. Therefore, the size of the p orbital will also increase. Any questions so far? If you have a question, please, you can ask. If you have a question, you raise your hand, then you speak. Thank you so much for cooperation. All audios are off. The class is so quiet, so we can listen and hear whatever I say. That's a good one there. Please don't forget, let your friends also enjoy the lesson. So share the links to your friends, wherever they are under the sun. Let them connect. Is that okay?
Yes, sir.
Thank you. Techno Spark 2.
Yes, sir.
Please, we want to know your name. Techno Spark 2. Sign in with your name so that we can know. I have Gabriel there online. I have James. I have Sam. I have Salon. Techno Spark 2. Please kindly change that to your real name. Okay, so kindly do that. And the next thing we want to look at is the differences between S and P orbitals. So at the end of it, you should be able to at least give 3 differences between P and S orbitals. Is that okay? Okay.
Yes, sir.
Salon, read the first one for us.
Okay. S orbital has spherical shape, whilst the P orbital has dumbbell shape.
Thank you. Hello, Sam.
Thank you.
Sam. Hello, Sam.
Yes.
Sam, please read the second one to us.
S orbital is unidirectional, whilst P orbitals are directional.
That is excellent. Samira, are you there?
Yes, sir.
Thank you. Take the third one.
For the S orbital, its electrons are closer to the nucleus. And for the P orbital, its electrons are far from the nucleus.
That is excellent. Let me look for other names. Hello, James. James. Hello, James. Hello, James. Oh. Ahinkra. Hello, Ahinkra. Kendra. Kendra, turn on your audio. Turn on your mic. So you can speak now. Take the fourth one. Kendra, we are talking about differences between S and P orbitals.
Okay.
So read the fourth one, the fourth difference.
Has no lobes. The S orbital has no lobes and P orbital has lobes.
Okay. So the S orbital has no lobes, and then the P has lobes. Thank you, Kendra. Gabriel. Hello, Gabriel. Hello, Gabriel.
Yes, sir.
Gabriel, please take the fourth one. Kendra has taken the fifth one, so take the fourth one.
For the S orbital, no degenerate orbitals.
Then the P.
For the S orbital.
Oh, Oh, James. Oh. Please turn off your audio. Turn off your audio if you are not speaking. Thank you. Thank you. Hello, Sam.
Hello.
Sam, read the fourth one, the fourth difference.
Okay. The S orbital has no degenerate orbitals, and the P orbital has degenerate orbitals.
Thank you. When we are talking about degenerate orbitals, from quantum numbers, when an orbital is subjected to a strong magnetic field, it splits. For example, the p orbital, what did we say? We said that it is directional towards the x, y, z axis. So that is telling us that when the x orbital is subjected to a strong magnetic field, it splits into 3. So I have that. So I have 1, 2, 3. And that is px, py, and then pz. And these are the ones we call degenerate orbitals. So they are orbitals that have similar energy. The d orbital in a strong magnetic field splits into 5. So it means that the d orbital has 5 degenerate orbitals. And then the f orbital gives us 7 degenerate orbitals. Take note of it. But the s orbital has no degenerate orbitals because we said that it is unidirectional. Take note. Then the lobes we are talking about, we are saying that the s orbital is spherical, just like that. But the p orbital looks like this. So that is the lobe of the p orbital. Then the other one to look like this. So these are the lobes we are talking about. So if you are asked to give 3 differences between S and P orbitals, you should be able to do that. And don't forget the shapes. Let's look at the similarities between S and P orbitals. Gabriel. Hello, Gabriel. Gabriel, are you there?
Sir.
Yes. Read the first one.
Point 1. Their sizes, or rather, increase as n increases.
Okay. Number 2. Kendra.
Both exist. Okay.
Thank you, Gabriel. Kendra should take the second one.
Okay.
Kendra, second one. Please off your audio if you are not contributing to the class. Off your audio. Thank you. Now, if you want to speak, you on it, you speak, then you off. Is that okay? Kendra, read the number 2 similarity.
Okay, second point is both exist in atoms.
Good, that is excellent. Sam, hello, Sam.
Yes.
Take the third one.
They both contain electrons.
These statements, are they true?
Yes, they
Are they
are.
true? They are true, yes. Because orbitals contain electrons in atoms. Orbitals exist in atoms. And we have already established that the size of the orbitals increase when n is increasing. That is the number of shells. So if I have helium, for example, helium has 2 electrons. If I add another shell to it, and then it contains an electron, this is no more the atom of helium, but this is the atom of lithium, because lithium has 3 electrons. If I add another electron, there's no more lithium. Identify that atom. Yes, Salom.
Beryllium.
Beryllium. So we have beryllium, that's 4. If I add another electron, there's no more beryllium. Which atom is that? Hello, Sam. Hello, Sam.
Hello. Hello.
Yes. Yes.
Please, the question again.
Which atom is that? From beryllium, I have added another electron, giving us 5 electrons. Which atom is that?
Boron.
Boron. That's good one. And so on and so forth. Okay. Let's look at electron configuration. Some of us might have known already, so let's review. Those of us who do not know, that is why we are here for you. You don't have to see it as anything difficult. It's very, very simple. We have electron there, which you know that electrons carry negative charges. And then the configuration here is from the word configure. So this is English word, configure. So let's go to English. What does it mean? If I say, Salon, configure these items, what should come to your mind? Hello, Salon. Salon. What should come to our mind? If I give you some items, let's say pencils or pens, then I scatter them on the table. Then I say, Salon, configure these pencils or pens. What should come to your mind? Hello, Salon, are you there? Okay, Gabriel. Hello, Gabriel. What should come to mind? Oh.
Sir.
Yes.
Draw.
Draw.
Yeah.
Configure these pens. Configure
okay.
these pencils. Hello, Samira.
Sir.
Samira, what does it mean to configure something? One
I
word.
think arrange.
Arrange. That is excellent. So arrange the pencils, arrange the pen. So arrange. Okay, off your audio. Gabriel, no, your audio. Thank you. Thank you so much. So Samira said to arrange. Then we go for that one. So if we say configuration, then it means arrangement. Arrangement of what? Electrons. So electron configuration means arrangement or distribution. Where are we distributing it? In the shells of the atoms, or we are arranging the electrons in the shells of the atoms. So if somebody asks me, what is electron configuration? And I know that configuration means arrangement, then it means arrangement of electrons. Where? In the orbitals of what? Atoms. Or in the shells of atoms, then I'm okay. I don't need to go and be worrying my head, memorizing. No. Are we there?
Yes, sir.
So, Salon, Samira, what is electron configuration?
Sir.
Yes.
It is the arrangement of electrons on the orbitals of an atom.
It's as simple. It's as simple. That is good. Hello, Salon, are you there? Hello, Salon, are you there? Sam. Hello, Sam.
Yes.
Oh,
I'm here.
What is electron configuration?
Electron configuration is the arrangement of electrons in the orbitals of an atom.
Good. That is excellent. Then the last one, Mohammed Awol. Mohammed Awol. Hello, Mohammed. Hello, Mohammed. Okay. Okay. Right. So it's as simple as that. So the electron configuration takes the form NL superscript X. So the N there is the principal quantum number as we know it from quantum numbers. And then the L here means the angular momentum. That gives us the symbol of the subshell or orbital. So then I can say S, I can say P, I can say D, I can say F. So those are the symbols. S means sharp. P means principal. D means diffused. And then F means fundamental. Now, at this stage, we'll only be looking at the configuration involving SPD. Then the X there, as I said, is the number of electrons in there. So if I say n equal to 1, and then L equal to S, and X is equal to 2, I can say that my configuration will be 1s2. So that is the first energy level containing s orbitals with 2 electrons, or there are 2 electrons in the s orbital of energy level 1 in that given atom. Hello, Clinton. Hello, Clinton. Hello, Clinton. Oh, okay, so let's continue. So with this, we can do a lot of such. So this is another example. This one is telling us that the s orbital is in the 4th energy level containing 2 electrons. That is the meaning of it. So if I say 2p6, then it means that the subshell or the orbital p is in energy level 2 containing 6 electrons. That is the meaning. Or there are 6 electrons in the orbital p, or in the p orbital at energy level 2 of an atom. This is the meaning. So if I have more orbitals and more electrons, I should be able to arrange that appropriately. So a quick reference here, the energy levels 1, 2, 3, 4. The main shell, as Salon mentioned earlier, we have the K shell, we have the L shell, we have the M, N shell, and so on and so forth. And what are the orbitals contained in? Energy level 1 contains the S orbital, energy level 2 contains S and P orbital, and then energy level 3 contains SP and D orbitals, and then the energy level 4 contains SPDF orbitals. Now, take note of this, very important. We said that the S orbital has no degenerate orbitals. So wherever I see S orbital, it can't split. It is as it is. So it means that at energy level 1, that is n equal to 1, I have only s orbital there. The s orbital takes a maximum of 2 electrons. That is why I said earlier that the first energy level, n equal to 1, will have 1s2. Then energy level 2, we have s orbital there, but we said that the p orbital splits into the px, py, and then pz. So energy level 2, we have 3 degenerate orbitals of p plus s. So inside here, energy level 2, we have 4 orbitals. And if each is containing 2 electrons, we'll have 8 electrons in that orbital. So how many orbitals are there in energy level 2? We have 4. And then there will be a maximum of 8 electrons. Don't forget. Salon, are you there?
Yes, sir.
I'm coming to ask you a question. How many orbitals are there in energy level 3? Salon, are you there?
Say yes.
Okay. How many orbitals are there in energy level 3?
I don't really understand this.
Okay. So let's take it
Yes.
again. Let's take it again. Thank you for that. That's excellent then.
Yeah.
In energy level 1, only s orbital that exists. So energy level 1, we have only one s orbital. Energy level 2, we have S and P. So we can also refer to them as subshells. So we have S subshell and then the P subshell. Now the P subshell contains 3 degenerate orbitals. And these 3 degenerate orbitals will also contain electrons. So that if I'm talking about the orbitals that will contain electrons, I will count 4 orbitals in energy level 2. I'll have the s orbital 1 and then 3 of the p orbitals. So 1 plus 3 will give me 4, isn't it? Salom.
Yes.
Are you okay?
Yes, sir.
And then I said earlier that the d orbital has 5 degenerate orbitals, or the d subshell has 5 degenerate orbitals. And then the p has 3. So if I want to know the total orbitals in energy level 3, what will I do? Yes, Salon.
You add them. You add the s orbital, that's 1. Plus the p orbital, that's 3. And the
Good.
d orbital, 5. That which will give you 9.
9. So how many electrons will there be? Each orbital carries 2 electrons. So what is the total number of electrons in the energy level number 3 in an atom?
18.
18. So if you have understood it well, what will be the total number of electrons in energy level 4?
How many orbitals are in F?
I'm talking about total number of electrons. F has 7.
Okay.
7, 5, 3, 1. So what is the total number of electrons? That would be in energy level 4.
14 plus 8.
So I'm coming.
Okay, that's good.
$32.
32. Yes, James. James, I saw your hand.
Yeah, I wanted to say 32 in the process of the calculation, but it seems he has answered. So let's continue.
Okay. So how many orbitals are there in energy level 4?
The orbitals.
Yes.
there'll be 7 orbitals.
No, James.
Okay. Yeah, okay.
Good. Good. You saw your mistake. Okay.
Yes, sir.
Okay. Now give us the right answer.
Yeah, there'll be 10 orbitals.
Oh, James, do the calc. This one is simple mathematics. This one is day-nursery mathematics. Gabriel, off your audio. Gabriel, off your audio. Please off your audios. James, you are still on the floor. Give us the right answer. Oh, James has run away. Hello,
No,
James.
please, I haven't run away, please. Yeah, I just muted, but we did.
Thank you. Thank you for being there. Okay, give us.
Yeah, me watching. Let me say, I watching from afar. Like I was really getting about because the question has been just posed on me. I'm getting confused right now. So please let me just take time here.
Don't get confused. It's very simple. Don't get confused. Don't get confused.
Yeah, the orbitals. Let me see. That's referring to the shells, right?
No, the orbitals are located in the main shells, and the main shells are the K element. Is that okay? So yes, we are saying that in the N shell, that is N main shell, that is this way, this one.
Yes, sir.
This one. Those are the K, L, M, and then N. Now within this K, L, M, N are orbitals, and those orbitals are containing electrons.
Yes, sir.
So in junior high school, you were told that the K shell has 2 electrons.
Yes, sir.
Now, quantum number came in to talk about the orbitals.
Yes, sir.
And we are talking about S, P, D, F orbitals.
Yes, sir.
And we said that the S orbital is only 1. So we can also refer to it as a shell or a subshell.
Okay, sir.
When we come to P, that is energy level 2, that is the L shell, we can say that the L shell has the S subshell and then the P subshell.
Yes, sir.
Now the P subshell is divided into 3.
3, yes, sir.
So if we say that the P orbital, then we can say that the P orbital has 3 degenerate orbitals.
Yes, sir.
So it means that we'll have, if we are talking in terms of orbitals, we can say that the P subshell has 3 orbitals.
Yes, sir.
And then the D will have 5 orbitals.
Yes,
then the F will have 7.
Yes, sir.
So what will be the total number of orbitals in the N shell?
So that'll be 2. Come on. Okay.
That will be.
Yeah, please, I'm coming. Like that'll be 4 plus 5. That'll be 9 plus 7. That'll be 14.
Oh,
hey,
James.
That'll be 16. 16. Oh, come on. That'll be 16. Also. But
hey, James.
Yeah, being a spectator is very, very fun, but coming to playing on the field, like, yeah, you really feel the pressure.
You know that, yes. Thank you.
Yeah.
Thank you so much.
Yeah,
Thank
that'd
you
be
so much.
16. That'd be 16 orbitals.
Exactly. That would be 16 orbitals.
Yes,
And
sir.
each orbital carries 2 electrons.
Yes, sir.
That is why we said that energy level 4, we have a maximum of 32 electrons in energy level 4.
Okay, sir.
Right.
You,
Thank you so much, James, for the contribution. Yeah, let's continue. Please, if you have any questions, you can ask. If you are not getting it, tell me and let's talk it over and over until you get it. Because if you get it, for life. So you can ask questions, you can seek clarifications, and so on. Now, James has gotten it. It means that wherever he goes to see questions of this nature, he will be able to respond appropriately. Let's look at the principles that we use for distributing or arranging electrons in the orbitals of atoms. Number 1 is the Abel principle. Now, since we said that as you move away from the nucleus, you are increasing in energy, Abel is saying that if you want to distribute electrons in the orbitals of atoms, you need to fill the lowest energy level before higher energy level. So the order of increasing energy level in the atoms are, we have 1s, 2s, 2p, 3s, 3p. This is energy level 1. This is energy level 2. And then this is energy level 3. And we said that in energy level 3, there are 3 subshells there. We have the 3s, then the 3p, and there comes 3d. So we can ask you to determine the number of orbitals in energy level 3. As we have already said, so now you know, James is aware. So if we are using the S P D configuration, the 1s orbital must be filled first according to Abel, because 1s orbital is the lowest among the orbitals in the shells of an atom. So you have to fill the 1s first. That is energy level 1. It's just like climbing a ladder. If you are climbing a ladder, you will not tell me that you want to go and climb from the top when you are on earth. You are standing on the ground. Then you say that you want to climb from, what are you going to do? Are you a bird? James. Hello, James.
Yes, sir.
James, are you a bird that you want to go and climb the ladder from the top down?
No, sir. You have to start from the bottom.
Thank you. So starting from the bottom, we will see it here as the lowest energy level. Why
Yes, sir.
is it the lowest energy level? The reason is that if you want to take an electron from energy level 1, you will need a lot of energy to be able to take an electron. It's just like somebody who is lying on the floor, and you want to help the person to stand up.
Yes, sir.
What are you going to do? You put in a lot of energy. Off your audio. Off your audio. Please, everybody, off your audio. Please, off your audio. You see, the person has collapsed. He or she has no energy of her own or his own. For you to lift that person, you will need a lot of strength, isn't it?
Yes, sir.
And that is why we are saying that
Yes, sir.
the electrons that are closer to the nucleus have lowest energy. To remove an electron from there, you will need a lot of energy. So Abbo is saying that for you to fill an orbital, you have to start filling from the lowest energy before filling the highest energy. Okay, so take note of that for the Abbo's principle. Or electrons enter and fill fully lower energy levels first before higher energy levels. And we are saying that the energies are increasing from n equal to 1 to infinity. Now, the reason why you have higher energy as you are moving away from the nucleus is that as you are far away from the nucleus, the effective nuclear charge, that is the attraction of the nucleus on the electron, will also be weaker. And if it is weaker, you can easily run away from the attraction force. Then we'll describe you as you having higher energy. It's just like your little sis or your little brother, and then your big sis or your big brother. When they hold you, which of the two brothers or sisters can you easily get off their grip? Samira. Hello, Samira. Hello. Oh, hello, Salon.
Sir.
Salon. Your little sis is holding you.
Okay.
And then your big sis is holding you. Which of the two will you get free easier?
My little sister.
Good, because your little sis has lower energy than you have. So you can easily run away from her grip. So we'll say that you have more energy than your little sis. That is why you can easily get off her grip. And that is what is happening here. So the electrons far away have very weak force from the nucleus. So we say that they have a lot of energy. That is why they can easily leave the attraction force of the nucleus. So Abbo says you have to feel the lower energy before higher energy. The next one, we have this arrangement, which I have already talked about. So we can have this example. So if I have the 1s, 2s, and then 2p, I can't go and be filling from 2p because the energy of electrons in the 2p are of higher one. They have higher energy. So I have to start as climbing a ladder. So I have to start from the lower energy. That will give me 1s2, 2s2. And because beryllium has only 4 electrons, I'll have 1s2, 2s2, but the 2p will be empty. Then if I have carbon, this is the distribution, 1s2, 2s2, 2p2, and then you continue concerning with regards to the number of electrons that you have. You can continue to infinity. Now, sodium has 11 electrons. So we have 1s2, 2s2, 2p6, and then 3s1. Please, you must learn how to write these. If I want to use the electron box configuration, then I can have for the beryllium, then I have my 1s there, 2s there. So I have my box. So 1s2 will have that, 2s2 will have that. So opposite spinning anti-clockwise, spinning clockwise. So any moving charge creates magnetic field. So within an orbital, there is a positive magnetic field and there's a negative magnetic field. So at the end, there is no magnetic field created in the orbital. That ensures orbital stability. That is why if you are using the electron box configuration, the electrons must have opposite spins. One half arrow up, one half arrow down. Some you can use double-headed arrow, 1s, 2s. So I can also have that. And then please, if you do it like this, using the double-headed arrow, you are not wrong. You are correct. Any question here?
Sir,
Yes.
I'm confused with this one.
The configuration.
Yes.
Okay. Which side? This one or the box?
This one. Not the box.
Okay.
Yeah.
Okay. We already said, if you are following, we said that the electron configuration takes the form of NL superscript X. And we said that the superscript X there represents the number of electrons in the orbital. Then the L there is the orbital. That is a type of orbital. And then the N here is the energy level of the atom. And the energy level is from 1, 2, 3, 4, 5, 6, and so on. Is that okay?
Yes.
And then the orbitals, we have S orbital, we have P, and then we have D orbitals. Is that clear?
Yes, sir.
So that, for example, if they say an atom has 5 electrons, that's why we say electron configuration, electron arrangement. Arranging the electrons where? In the orbitals. What are the orbitals? S orbital, P orbital, and so on. And every energy level has an S orbital. Are you there?
Yes, please.
So the first energy level from junior high school, you were told that the first shell, that is the K shell, has only 2 electrons. Is that clear? Please off your audio. Hello, please off your audio. Please off your audio so that Samira will understand. Please off your audio. Hello. I want Samira to understand before I close. So please off your audio so that she will get it for me. Okay. So junior high school, we were told that the first shell has 2 electrons. And these are the rules that is governing the arrangement of electrons. Please off your audio. On the screen. Samira, please off your audio so that there will not be background. Each of the numbers. Howard, off your audio. Good, thank you. Okay. Samira, are you following?
Yes, please.
Okay. So we said that energy level 1, that is N equal to 1, represent the K shell. And the K shell is taking a maximum of 2 electrons. And the orbital in the K shell is the S orbital. So if we are using our general expression as N L superscript X, and then N is 1, L is S, and number of electron is X, then I should represent the configuration as 1s power 2. So the 1 here is telling us that we are in energy level 1. The S there is telling us that there is S orbital in energy level 1. How many electrons are there in the S orbital in energy level 1? Samira?
2.
2. So I say 1s2. Is that okay?
Yes.
Is that
Yes.
Samira?
Please, yes.
Are you sure?
Yes.
Can we continue?
Yes, sir.
Yes, James. Yes, James.
Yes, sir.
Please, one at a time. Please, one at a time. Yes, Clinton. Hello, Clinton.
Hello, sir.
Yes.
Well understood.
You don't understand?
Well understood.
Okay, that's excellent. Yes, hello, Samira.
Sir, for the sodium, like you see, when you are arranging for all, you have S before the P. But why is it that for the sodium, S is the last?
Is the last one. Good. That's a great observation. That's a great observation. From junior high school, you said that this is the K shell, isn't it?
Yes, sir.
Hello. That K shell, here we are describing it as energy level 1. And then you also talked about, what is the next one?
L shell.
L. And L shell, we have energy level number 2. That is
2.
N equal to 2. Is that okay?
Yes.
So for the sodium, if I put a line here, this is N equal to 1, sorry, N equal to 1. If I put a line here, this is N equal to 2. So energy level 1, energy level 2, is that okay? Samira?
So
No.
yes.
Now, in energy level 2, if you are following carefully, we said that it can take a maximum of 8 electrons. It was James answered this question, and then Salom also answered, if you are following well. So if the second energy level, we have 2s2 and then 2p6, that is the end of it. That energy level is full. So we have to continue in another energy level. That will be the energy level 3. Are you there?
Yeah.
So every energy level has an s orbital, and the s orbital is the lowest energy. So we have to fill that one first. As you can see it here, See, can you see this?
Please, yeah.
So it means that the last electron in sodium is in the 3rd energy level. And that is the s orbital. Because you have to fill the s before p. So if the s is not full, you cannot fill p. Samira, are you there?
Yes, sir.
Now look at this one. Look at magnesium carefully. Magnesium has 12. So let's fill it. Help me. Samira, help me. Let's fill it.
Okay, 1s2.
Good.
And we have 2s2.
Good.
2p6. And 3s2.
Now, that is excellent. Help me with aluminium.
Okay. 1s2. 2s2.
Good.
2p6 and 3s3.
3s. We said that each orbital carries a maximum of 2 electrons. So the 3s here will take 2. What is left? What is left? How many electrons are left?
1 electron.
1. So because the 3s is full, we have to go into 3p. So the last electron there will occupy the p orbital. Are you there?
Yes, please.
So the s. So let's summarize. We said that the p has 3 degenerate orbitals. So it means that the s orbital will take a maximum of 2 electrons. The p will take a maximum of 6 electrons. The g will take a maximum of 10 electrons. And then the f will take a maximum of 14 electrons. So if the s orbital is full, then you have to enter the next orbital after s. Are we there?
Yes, sir.
Okay. If you are there, Samira still, help me do this one. 14, silicon.
Okay, so 1 is 2. And 2 is 2. 2 is 6.
2.
2p6, sorry.
Good. 2p6.
Then think 3 is 2. 3p2.
Good. Excellent. Now you got it.
Yes.
You got it.
Yes.
Yes, you got it. That's excellent. So long as the 3p is not full, you cannot enter any other orbital until 3p has its maximum electron of 6. Is that okay? Is it okay now?
Yes, sir.
Hello?
It's okay.
Okay, that's good. Thank you so much. Any other question or clarification? Please don't hesitate. So let's look at the next law, Pauli's exclusion principle, that tells us that no 2 electrons in an atom can have exactly the same energy, or the total number of electrons that can fill any one orbital must be 2, and they must have opposite spins, which I have already indicated that if you are using the electron box configuration, you have to have an up arrow and then a down arrow. That is what Pauli is saying. And we have already expressed the fact that each orbital will have maximum of 2 electrons. Is that okay?
Yes, sir.
Okay. So we have already expressed Pauli's exclusion principle. So if it is a question, the question can specify that you should use electron box configuration. So that is what you have to do. So how do I answer questions here? The question can say use the electron box to draw the electron configuration of, say, sodium. So you use that. If they say you should write the electron configuration, then you have the 1s2, 2s2, and so on and so forth. If it is detailed, the detailed, you have to indicate the degenerate orbitals as px, py, and then pz. And don't forget, each will have 2 electrons. So let's look at the last rule for configuring electrons. So with the Pauli's exclusion, we can use this to illustrate. Samira, are you there?
Yes, sir.
Let's do this one. Help me do argon, that is 18. Let's write. So let's write 1s2, 2s2, and so on. Oh, Samira. I want to be sure that you really got everything before we sign off.
Say.
Yes, Alon.
Can I try?
Okay, that's excellent.
1s2. 2s2. 2px2.
2px2.
2py2, 2pz2, 3s2, 3px2, 3py2,
Oh, sorry.
3py2, and 3pz2.
So the total electron here will be 18. So this is the detailed form of writing. But if it is not, then I can have 1s2, 2s2, 2p6, 3s2, 3p6.
Then it will be, then,
Is that okay?
okay, yes, sir.
Yes. So that's all. That's all. Is it difficult?
No, sir.
Okay, that's good one. A hearty no, sir. So it is so simple. Last one. Last one. Hans' rule of maximum multiplicity. This one has to do with degenerate orbitals. So if you are filling the degenerate orbitals, let's say we are using the electron box. That is where the problem is. I say 2p6. How do I distribute this one? So Hans is saying that if you are filling degenerate orbitals, you must fill them singly with parallel spins before you pair with opposite spins, like that. Are we there?
Yes, sir.
Hello?
Yes, sir.
That is if you are using the electron box configuration. But if you are just writing, nobody will hold you responsible for writing 2p6. But if you are writing using the electron box, you are in trouble. You have to take your time. Is that okay?
Yes, sir.
Yes, sir.
So if, for example, I have 4 electrons, if I have 4 electrons to be filled in the p orbital, I'm going to have 1 there, 2 there, 3 there. Then the next one will pair with opposite spin. This is correct. If you do it as this, that, and then this one, you are wrong. So you have to fill singly first before you pair. And they should have opposite spins. That is Pauli's rule. So in electron configuration, all the 3 rules must come to play. So the reason is that, for example, if you are following carefully, I said that there are magnetic fields within the orbital as a result of the spinning of the electrons. So let's say I put the 2, I have 4, so I put 2 there. If I put 2 there, like this, 2 here, 2 like that, you see that these are degenerate orbitals. They have similar energies. This one is empty. This empty makes the orbital unstable. So you have to distribute it as uniformly as possible. So to avoid orbital instability or to ensure orbital stability, you need to distribute them as much as possible. They should be as far away as possible from one another so that nobody has anything to do with nobody. Everybody is in his or her lane. don't interfere me. So you have to be as far from me to avoid any interference. That makes the orbital stable. So the explanation is here that every orbital in a subshell is singly occupied before any orbital is doubly occupied by electrons. All of the electrons in singly occupied orbitals have the same spin to maximize total spin. Electrons have the same charge and therefore repel one another. Is that correct?
Yes,
Is that
sir.
correct?
Yes, sir.
Yes, sir.
So to avoid that repulsion, they have to move away from each other in space. That is why if I have, say, 3 electrons, you be here, you two be here, you two be there. Then we have peace. Is that okay? Any question? Any question? Okay. So to do this in a set of PDF orbitals, they must occupy different orbitals so that they are in different regions of space. Orbital stability is achieved by so doing. So with the degenerate orbitals, please, you have to fill singly before you pair up, like that, to ensure orbital stability. Right, so if you want to follow me, we can be here together until daybreak. So enough for the day. Too much of it is its evil thereof. This is Joy Learning Channel with teacher and you. And today we have discussed orbital shape and electron configuration. Now, any question that will ask you to draw the shapes of orbitals P and S, you should be able to do that. Any question that will ask you to write the electron configuration or draw the electron configuration using the electron box, you should be able to do that. If you have any issues hereafter, please don't hesitate to get to us. We are always there for you. To enjoy learning chemistry, just go on Joy Learning Channel and enjoy chemistry. Thank you so much for making it. Show your faces. Let me show your faces. Let me see your faces before I sign off. So I have James Clinton. Yep. Please turn on your videos. Let me see your faces before I sign off. Oh, Clinton is there. Yes, James. James. Butchie. Yeah. Yes, James. Oh, okay. So some have left. It could be that their data is run down. So sorry about that. Please, this is Joy Learning. Keep learning. Bye-bye.